There we go.
There we go. We got it,
Okay.
Kristen.
Well, firstly, I'd like to thank you all for coming, and I'd like to thank you for the opportunity to present today. So my name is Chris Howorth. I'm with the company Veolia. I'm based in Vancouver, and I'm here to talk about wastewater treatment and the technologies involved in that. So what I'm going to present to you today is, firstly, I'm going to introduce you to the company, to Veolia. I'm going to talk a little bit about the big picture on wastewater treatment, some considerations at a high level, and then I'm going to get into specific technologies and case studies relating to those technologies, and then going to finish up with some time for questions. So, introducing you to Veolia. Veolia is a very large company. It employs over 200,000 people all over the world. We have offices in over 100 countries, and we're active in 3 areas. Solid waste, so everything from collecting solid waste through processing it to recovering materials from solid waste. Energy, Dalkia is a Veolia subsidiary company. Dalkia is involved in electricity generation, and they've recently built 2 plants in British Columbia, one in Merritt and one in Fort St. James, producing electricity from forestry waste, each of them 40 megawatt plants. They also do heating and cooling networks. So that's the sort of thing we do in energy. And then water. Water is the biggest part of our company. It's about half of our revenues. And really, if there's something to do with water, then Veolia probably does it somewhere in the world. And obviously, that's the subject for today, so I'll be getting more into that. The interesting thing is where these areas overlap. So, for example, where water and waste overlap, you have things like co-digestion, taking high-strength waste from industries and co-digesting that with municipal sewage sludge, for example. Where waste and energy overlap, you have things like biogas generation from organic waste, food scraps. And then where energy and water overlap, you have things like heat recovery from sewage. So the common thread through all of this, and indeed the common thread in Veolia, is resources. Another thing that's fundamental to the company is innovation. Veolia spends a lot of money on research and development, and we do that in our own research facilities with our own staff, as well as through collaboration. Really, the objective of all of that is to improve the sustainability, the performance, and the efficiency of our products and services. So a good example of the collaboration we're doing, here actually on Vancouver Island, the photograph on the bottom left there you can see is a trailer parked at Shawnigan Lake, just up near Duncan, further up the island. And in that trailer, you can see the photograph on the right are 3 different treatment technologies for processing lake water into drinking water. We're doing that work with an organization called ResoWaterNet, that is NSERC funded, a National Sciences and Engineering Research Council of Canada. And the purpose of that work is to investigate drinking water treatment processes that might suit small communities in Canada and indeed further afield. The part of Veolia that I work for is called Veolia Water Technologies. And the clue is in the name. It's all about water treatment technology, drinking water as well as wastewater for municipal and industrial applications. Veolia Water Technologies has over 350 proprietary technologies, our own patented processes. And we also offer other manufacturers' technologies as well. So that gives us access to a huge range of different technologies. And that's important for 2 reasons, I would say. One is it means that when we're looking at solving a problem for a customer, we have this huge range of technologies to look at and work out which ones apply the best. It also means that we can put individual technologies together. A treatment plant is a combination of unit processes. So putting those together is key, integrating those unit processes into a complete operating plant. The company in Canada, Veolia Water Technologies Canada, is headquartered in Montreal, over in Quebec, founded back in 1948, now employs about 250 staff. And I've got a video here. Fingers crossed this is going to work. I'm going to tell you a little bit more about the company. Okay, good. So hopefully that gave you a bit of a sense of the company, all the different things we do, and some of the references that we have in Canada. So now focusing in on British Columbia. These are the plants where our technology is installed in British Columbia. Most of these are municipal plants. There's 1 or 2 industrial plants in there. And most of these are wastewater treatment plants, but there are 1 or 2 drinking water treatment plants in there as well. So it gives you a sense that really we're all across Canada, but also specifically that we've put in quite a lot of technology in British Columbia as well. So that's it for the company. Now, the second thing I wanted to talk about was this big picture considerations for wastewater treatment. Just a few sort of high-level ideas. So in the past, perhaps, wastewater treatment was primarily about compliance with regulations at the lowest cost. That mindset is in the process of changing now to perhaps focusing more on value. So what can you do with a wastewater treatment plant? Now, of course, value is subjective. Different people have got different feelings about what's valuable. I would point to a few things. Resource recovery is increasingly of value to people. Resources can be the water itself, wastewater reuse. It can be heat, it can be electricity, and it can be nutrients. But basically, there's all sorts of things in wastewater which can be valuable, which can be useful to recover. Another important consideration when we think about value is integrating the wastewater treatment plant into the community. We all produce wastewater one way or another, and it's got to go somewhere. So you need to do something with it that's appropriate. But maybe you can do more with it than just a wastewater treatment plant. Maybe you can build a treatment plant that's also underneath a park or in a building. There's all sorts of opportunities to get more for your money. So integration into the community is also an important value that we're seeing more of these days. And I would say that it's really the job of the industry to go from the not in my backyard kind of philosophy where frankly we'd just rather that it was out of sight and out of mind and the further away the better, to having a bit more pride in it. As I say, we all do it. It's, so as a community, we should be responsible and value it and really be proud of what we're doing with it. Treat it as well as we can and do useful things with it. Then we can take a bit more pride in wastewater. Technology enables that. And technology is continuously evolving, just like the industry, and becoming more and more efficient. So some examples of efficiency, you can see here on the photograph, this is a fairly typical wastewater treatment plant. In the yellow box, you have white circles, 4 white circles. Those are primary clarifiers. It's a very conventional technology. It's been around for many years, many decades, and it works on gravity. The inset graphic there you see is an example of one of our technologies, a Hydrotech filter. That does the same job as those primary clarifiers, but it does it in 1% of the footprint. So efficiency can be about compactness. It can be about space efficiency. So you can see the equivalent performance in those little red rectangles there, 1% of the land area. Another area of efficiency would be energy efficiency. Modern treatment processes are forever getting more energy efficient. And indeed, there are some treatment plants today that export energy to the grid. They are net producers of electricity. That is possible today. It is happening today. And another area of efficiency would be operation and maintenance, making these processes more reliable, more flexible, and easier to operate, more highly automated, so making the job of operators easier. Technology is really fundamental to a wastewater treatment plant project, and you can look at it in the 80-20 rule. So in terms of cost, the actual core technology is not the bulk of the cost of a wastewater treatment plant project. It's concrete, it's roads, it's buildings, but the technology itself is about 20% of the cost. When you look at the value of that technology, however, it's the other way around. It's more like 80% of the value because it's about performance. It's about achieving your treatment objectives. It's about avoiding nuisance to neighbors. It's about operating cost over the next decades. And that's where the value is, and technology is what delivers that. So therefore, you have to select the right technology to meet your objectives, and you have to integrate specific technologies together to form a treatment plant that does the job you're looking for it to do. So now looking at some specific technologies, and probably most people here are familiar with the background, but just to go over that very quickly. Westside Solutions issued a request for technical information at the end of last year. We responded to that, and the first thing we did was look at this long list of technologies we had, these 350 of our own and technologies from other manufacturers too, and shortlisted a few to present. We couldn't talk about all of them, so we had to choose a few which seemed most interesting, most relevant to this area. From that, then that was the basis of our submission. This is a shortlist of that shortlist, so we couldn't even present all of those today. So we've had to really narrow it down. So we've got 5 to present to you. And these are those 5 that I'm going to be talking about today, the specific technologies and the case studies with them. The first 3 are to do strictly with the wastewater treatment at the wastewater treatment plant. The 4th is to do with stormwater treatment, and that can happen actually at the treatment plant or out in the collection system in the sewerage network. And the 5th is around the biosolids, the sludge treatment. So a bit of a flavor. Hopefully this gives you a bit of a cross-section of different processes. So looking at the first, a lot of acronyms in wastewater treatment, and I apologize for that, so I've tried to spell them out. MBBR DAF, moving bed biofilm reactor, dissolved air flotation. This is actually 2 processes, and it's a good example of integration of 2 unit processes into a treatment solution. What MBBR DAF gives you in combination is secondary effluent quality. And that means that meeting the federal standards of 25 milligrams a litre of total suspended solids, TSS, and 25 milligrams a litre of BOD, biochemical oxygen demand, federal standard secondary treatment. You can also remove ammonia and indeed total nitrogen with this technology as well. It's been used at treatment plants really from the very small to the very large. It is extremely flexible, suiting all different sizes of treatment plant. And the key nature of the technology is simplicity. And hopefully that will become clear as I explain a bit more about how the technology works. It works on the attached growth principle, biofilm principle, where microorganisms attach themselves to a surface, and they are the things that break down the wastewater. So the key is to give them a surface to grow on, and the bigger the surface, the better, because then you get more of them in a given volume. So by putting them on this little plastic media that you can see in the photograph here, and I've got some examples. This is the one that you can actually see in the photograph, so really quite small, and we've got different types. Here's another one, a little bit larger. Horses for courses, really. There's different applications for the different types. That gives you a very large surface area in a very small volume. So you can hold a lot of microorganisms and be very efficient in your treatment. A small plant that can treat a lot of wastewater. It also gives you robustness, because if you've got a lot of bugs in the system, a lot of microorganisms, then that can tolerate variations in load. The process can tolerate toxic shocks if you have a spill of some industrial chemical that comes into the system, and it can tolerate hydraulic variations as well. So a very robust process. So how it looks, this combination of processes, on the left, you see a tank. That's where the MBBR process happens, moving bed biofilm reactor. And that's full of these little plastic media. Air is pumped into the bottom of the tank to give the microorganisms the oxygen they need to break down the sewage. And the plastic media is held in the tank by sieves. And it is a very simple process because the wastewater simply flows in one end and flows out the other treated. There's no returning of sludge or controlling sludge ages or anything. Very simple technology. It also doesn't require a primary treatment step up front, unlike many technologies. All you need is a pre-treatment with screening and grit removal. And then what happens is the biomass growing on these surfaces consumes the wastewater, reproduces more microorganisms. So ultimately that biofilm grows thicker and thicker, and some of it will slough off. As it sloughs off, it flows out of the tank, out of the MBBR process, and into the second process, the dissolved air flotation process, where it is separated from the water and wasted as sludge. That is important because it means that you get the secondary effluent quality you're looking for. So you remove the biochemical oxygen demand, BOD, in the first tank, and then you remove the solids in the second tank. Another important thing there is that BOD, biochemical oxygen demand, in wastewater is both dissolved and particulate. There are little particles of organic material as well as in solution. So the first tank removes the dissolved BOD. The particulate BOD flows straight through. The organic material that is particulate flows straight through to the DAF process, where it is removed physically. Now that's important for 2 reasons. The first is that it's much more energy efficient to remove BOD physically through dissolved air flotation than biologically, as many treatment processes will do. It needs far less air, but producing air is very expensive. It's the single biggest cost at most wastewater treatment plants. So if you can avoid using all that air by letting the particulate BOD go straight through the biological process, then removing it physically, you save energy. The other thing is because you haven't broken it down biologically, that sludge that you remove from the process has got a higher energy value, a higher calorific value. So if you digest that sludge, you recover more electricity from it. If you make biogas, you get more biogas from it. So it's less energy to break down the wastewater and more potential to recover electricity. So the process, just really in summary on this one, is very cost effective. Compact process, small tanks, very easy to integrate into different sites, meaning a low capital cost, and very simple to operate, meaning a low operating cost and the energy as well. This makes it a very operator-friendly process. And I do want to stress that a wastewater treatment process is really only as good as the people who operate it and the ability they have to operate it, and that's partly theirs, but it's also partly the technologies that you give them. So we have to try and make their lives easier by giving them technologies that are easy to operate and reliable, because that's where the rubber hits the road. And if you're going to have a successful project over the long term, the guys operating it have to do a good job, and girls. So that was the MBBR. Now looking a little bit more at the DAF. How does the dissolved air flotation process work? So you can see on the left, you have the little bubbles. So where they come from, I'll just use the pointer here. Hopefully that's going to work. Here you have an air saturation process on the top left. What happens in here is you bring in treated water and you dissolve air into it under pressure. We use jet pumps for that. So now you have a solution of water with air under pressure. When you bring that solution around to here and it then reaches atmospheric pressure, because this tank is open to atmosphere, the bubbles come out of solution, just like taking the lid off a soda pop bottle. As those bubbles come out of solution, they attach themselves to solids and float them to the surface. If you've ever added Coca-Cola to orange juice, then you'll know that the pulp rises to the surface. Looks terrible. It looks just like sewage, actually, but it tastes great, so maybe somebody try. So what you now have is a layer of sludge on the surface here, and that's scraped off using a mechanical scraping device. The water flows to the bottom of the tank and is removed underneath, and that's clarified at that point, some of it going back around to make air, to make dissolved air in the water, and the rest treated at secondary effluent quality. So the dissolved air flotation process, we call it our speed flow technology, is very compact. It's relatively recently developed technology, and it's improved upon dissolved air flotation. So you can see the numbers on the diagram at the bottom there. It is a very efficient dissolved air flotation process in terms of the flow rates you can put through it, and therefore the space it requires. And that also makes it cost effective because there's not so much civil work to put it in. The sludge that you scrape off the top is at 3% solids, and that means that you can put it into a digester or wherever it needs to go without necessarily having to thicken it. So that can avoid an entire unit process, a thickening process. It's also chemical free, so you get this good performance without having to buy chemicals and therefore the operating cost. It's a very well proven technology, MBBR. Developed firstly back in the 1980s. We invented the technology back in the 1980s. The first commercial plant went in 1989, and it's still running with the same plastic media in it. So these things haven't been replaced. There are over 1,000 operating around the world and 11 in Canada. You can see one in the bottom right there in Quebec, Noyan, a relatively small plant, but as I said earlier, everything from the very small to the very large. At the small end, you can put it in package systems, already installed into modular buildings. At the bigger end, obviously, it's going to be more of a custom solution. The case study I'd like to present on this one comes from Norway. You can see the numbers there, relatively large plant. From the request for technical information, RFTI, that Westside Solutions put out, the top flow range on that was 50 million litres a day, MLD. And that's what you see, this one pretty much getting to the top end. This community is, in many ways, reflects a lot of the nature of Greater Victoria. It's next to the waterfront, near the ocean, limited space. In this case, they had an existing plant, and you can see that in the photograph in the back there. That building was the existing plant, and they couldn't expand that plant. It was already hemmed in. So that means they had to, because they had to upgrade the plant for effluent quality reasons, they needed something compact to fit into that existing space. Okay, so a second video here, just to show you a bit more about that plant. And I should say, this is in Danish, but for those who don't speak Danish, there are English subtitles, so hopefully you can follow along. Oh, sorry. Let's get one there.
I Norge bor det nærmere 5 millioner innbyggere. Vest for Oslo ligger Drammen. Byen kalles Elvebyen og har over 60 000 innbyggere. En by på denne størrelsen trenger et effektivt renseanlegg for å holde elva og fjorden ren. Ved Drammensfjorden ligger Solumstrand renseanlegg. Anlegget var i utgangspunktet bygget med kun kjemisk rensing. Ifølge EUs vanndirektiv skal avløpsvannet nå også behandles biologisk. Det var ingen mulighet til å utvide størrelsen på renseanlegget. Den tekniske og økonomisk riktige løsningen var å øke kapasiteten og innføre biologisk rensing innenfor eksisterende areal.
Vi i Krüger Kalnes har tilgang på en mengde patenterte teknologier. Dette gjør at vi kan bygge renseanlegg med ekstremt kompakthet og en fantastisk fleksibilitet. La oss nå se hva slags utgangspunkt vi hadde på Solumstrand. Her ser vi 6 sedimenteringslinjer. Samlet kapasitet er 3000 kubikk i timen. De øverste delene de konverterte vi til MBBR. De 2 nederste delene de lagde vi til Actiflow, og på den ledige plassen vi fikk imellom, så tok vi det planlagte kjemikaliebygget og la i den ledige plassen. Byggherren fikk en også god besparelse med hjelp av Actiflow.
Med MBBR kan biologiske rensetrinn bygges meget kompakte og kostnadseffektive. Metoden bygger på at biomassen sitter på bærere i et luftet basseng.
Kalnes MBBR er en norsk oppfinnelse, utviklet ved NTNU i Trondheim, som har gått sin seiersgang over hele verden. Actiflow er et patent eiet av Veolia Water. Actiflow den bruker mikrosand, som gjør at vi kan bygge ekstremt kompakte sedimenteringsbasseng.
Ved hjelp av mikrosand kan den kjemiske fellingen foregå på et ekstremt lite areal. Actiflow renser vannet på under 10 minutter, noe som er verdensrekord innen kjemisk felling.
Vi vant jobben på Solumstrand, ikke fordi vi var billigst, men fordi vi leverte en løsning med høy rensegrad, kompakt anlegg, en stabilitet i anlegget og en hurtig oppstart.
Høsten 2008 startet ombyggingen av Solumstrand.
More value the strategy, there's resource recovery. Sludge is an energy, think bioplastics. Think responsibility for job safety and training. Footprint and economy, sustainability. The public debt is so high, water run is so low. Looking at the higher rates to tell you what you should do. When the antis start complaining, I show them my footprint. Speak with grand eloquence, 3 words come to me. Service, value, responsibility. Service, value.
Det nye Solumstrand sto ferdig i mars 2011. Ordføreren i Drammen foretok den offisielle åpningen.
Nye Solumstrand renseanlegg representerer en ny epoke. I dag har Drammen en ren elv, og det har vært et solid bidrag inn i byutviklingen.
Service, value, responsibility.
There you go. For those who've never heard rapping about wastewater before, something new today. Something I should point out is that didn't have the dissolved air flotation process in it. Some of you might have noticed that. It had a different process called Actiflow for doing the clarification. I'm going to be talking a little bit about that in just a few moments. But the MBBR process was the one I was talking about. Okay, so now the second of the 3 technologies I wanted to present to you on wastewater treatment. Biological aerated filtration, BAF. This technology produces higher effluent quality still than the MBBR. This will produce tertiary quality effluent. It's suited for medium and large size plants, so 20 million litres a day being in the middle of the flow range that Westside Solutions asked us to look at. And really the key characteristic of the technology is efficiency. And that is efficiency in terms of effluent quality, also in terms of energy, and I'll explain how that works, and space. It's a very compact process. So how the technology works, it's a modular process. Here you can see 2 concrete tanks divided into cells. What you have inside of these tanks in this area is Biosolids plastic balls, or polystyrene balls, sorry. I'm not sure if people can see that on the video, but this is a bag full of those things, styrofoam, little styrofoam balls. And what they do is they go in this cell and they're held down by a ceiling.
No, sorry. You've been here every day. You know you need the microphone.
You said there'd be chips, though.
Not on.
I can repeat the question.
Okay. Firstly, sorry to interrupt, but is this process that you're discussing now, is this in addition to the MBBR, or is that replaces that?
Okay, so the question is this a separate process to the MBBR, or is it something that you do together with an MBBR? No, it is a separate process. So both of those processes, the MBBR and the Biosteer process, are for treating wastewater biologically. So this does the same job, only differently.
Okay, so you wouldn't have, this wouldn't be like an inline process?
No, this would not. This is a separate technology entirely.
Okay.
Yes, you're welcome. Thank you for the question. So how this works, you have these styrofoam balls in this tank held down by a ceiling. The wastewater flows in from the bottom down these blue pipes and rises up through this bed of styrofoam balls. And that filters the wastewater. It also provides a surface for the biofilm to attach to. So again, it's an attached growth biofilm process like the MBBR. And that gives you the same benefits of particulate BOD removal physically, and therefore high energy sludge and energy efficiency. That's one of the reasons why this technology is so energy efficient. The other reason is because, as well as bringing the wastewater into the bottom, you have air, and that's these orange pipes in the diagram. And so the air and the wastewater rise up through this filter media, and that gives the oxygen a very long time in contact with the microorganisms. So you get very efficient energy transfer, or oxygen transfer, sorry. So the treated water rises out of the top, and that gives you a clean environment. Periodically, these cells are taken offline individually and backflushed by reversing the flow. So that treated water is allowed to flow down, back through the filter. That causes those styrofoam balls to separate, jiggle around, and wash out the solids that have been trapped in there, and that is then sent back to a primary treatment process for clarification. There is no downstream process to the Biosteer in terms of clarification because it filters, so there's no DAF, to use the analogy of the MBBR. Another question? Far away.
And actually, if this could be it, and we can let Chris get through his presentation, that would be great.
Okay, just one quickie. Do those styrofoam balls break down over time?
No. No. Our experience with operating these things over many years is that they don't need replacing. No. So that's the process. The benefits of the process in summary: very energy efficient. I've said that a few times now. A quarter of the air of conventional and activated sludge. And aeration is the biggest single energy consumer at most plants, therefore very energy efficient, very cost efficient over the long term. Life cycle costs, very cheap. And that treated water on top gives you inherent odor control. Also extremely compact. I believe this is actually the most compact treatment process that achieves these effluent qualities that's available today. And because it's compact, it gives you a small footprint, cheap civil costs as well, construction costs. And you can see the cell there in the photograph. There are 4 operating in Canada today, 3 in Ontario, 1 in Quebec, I'm going to be giving you an example of the Ontario plants as the case studies, and about 150, more than 150 operating around the world. So these are the two that I'd like to talk about in Ontario. No video this time, sorry. No rappers. But you can see the numbers there when they were done and the capacities. They were both installed for very similar reasons. The treatment plants, existing treatment plants, needed to be upgraded to treat more wastewater capacity and quality reasons as well, discharge, effluent quality. Both of those treatment plants had limited space on site. This one, Kingston, is on a hillside. You can see the process incidentally up at the top here. That's the Biosteer process up at the top. But because it's on a hillside, construction is expensive, so footprint becomes important. The other plant was surrounded by very tight neighbors, limited space to expand. And both of them had an energy vision to use less, both of the municipalities, use less energy, produce more electricity from sludge. And that drove them to look at these technologies. What they did was a technology selection step. So one of the procurement methods that municipalities use is to firstly select technology through a competitive evaluation process. Then when the municipality has homed in on a specific technology, then have an engineer do detailed design for the specific site based on that technology before going out for contractor bids. And that means the contractors get a very clear idea of what they're trying to build because it's all been based on a single technology after that's been selected. So this is the evaluation criteria they used in Kingston. And you can see cost at the bottom was actually the single most important thing, but really it breaks down into thirds. You can say cost, performance, and then operation and maintenance. So this is the performance before the Biosteer process. On the blue line, you can see the target that they were trying to get to, and this is total suspended solids is the axis, and that's 15 milligrams a litre. That was the effluent target that the municipality wanted to achieve. It had a compliance, like the federal standards, of 25 milligrams a litre, but you can see sometimes their numbers were getting over 20 milligrams a litre. And if you're an operator of a treatment plant, that's beginning to ring alarm bells. That's too close for comfort. So after the Biosteer process went in, you can see they got very comfortable. Far, far below the design target, averaging below 5 milligrams a litre. Very good quality effluent. And they did that using less energy and with the potential to generate more electricity from the sludge. The third of the wastewater treatment technologies I'd like to talk about today is membrane filtration, and specifically the use of membrane filtration for tertiary filtration at the back end, the last step in a treatment process. And UF is ultra filtration. It's a category of membranes, and those are the ones you're going to see mostly in wastewater treatment. Some folks might have heard of MBR, membrane bioreactor. Very similar acronym, but totally different process to MBBR, so a lot of folks get tripped up on that. Membrane bioreactor, MBR, they use membranes as well, similar kind of product, ultrafiltration membranes. Using membranes for tertiary treatment as a last step in a train of treatment processes is all about producing high quality effluent. These membranes will actually produce Class A reuse quality effluent. A very modular technology, so you can use it from the very small plants to the very large plants, and as I said, key characteristic, effluent quality. How they work, they are a barrier, a physical barrier to contaminants. And you can see a microscope image on the bottom left there. It's a porous barrier, so the contaminants are held on the feed side, on the dirty side, if you will, and then the clean water is able to squeeze through those little pores and out treated. I've got an example of one here. It looks a bit like a spaghetti, a thin spaghetti, and it's got a hollow center where the wastewater goes in. Those spaghettis are put into a module, a pressure vessel. You can see one here on the top top right. And those modules are then assembled onto a skid in a bank of modules, and that's what ultimately you feed the wastewater to. Oh, yes, thank you. There are various different ways of applying membranes. I mentioned MBR as being one, tertiary filtration is another. The benefits of putting it at the back of the process as a tertiary step is that because it's it's following a number of treatment processes upstream, the quality of water that you are filtering with the membrane is already quite high. It's treated to a secondary standard before it even gets to the membrane. And that's good because membranes can be quite sensitive. It also means that you can be very flexible in how you use this system, this unit process in your plant, because really it's driven mostly by reuse of water. So in the winter, perhaps you don't want to produce as much really high quality water. You might be happy to discharge half of your water into the environment, and you only need half of it for reuse in the winter. In the summer, you might want as much reuse quality water as possible. By doing it like this, you can turn half of the membranes off, all of the membranes off, whatever you want. It's very flexible in how you operate it. And that's also good because when you have a peak event, a heavy rainfall, for example, you're not trying to filter all of the water. You can bypass this step because if it's already been treated to secondary quality, then you can discharge some of that water into the environment to handle those really high hydraulic peaks. We represent another manufacturer for membrane technology. That manufacturer is X-Flow. They are, according to Global Water Intelligence, an independent organization that looks at these things, the market leader globally for this type of membrane, ultrafiltration. Many hundreds of installations all over the world. We represent them in Canada, and we've installed 6 plants with their technology in Canada, 3 for drinking water treatment, 2 for industrial, 1 for municipal wastewater. And those sizes of plants, you see there, 2 to 11 million litres a day. So the case study I'd like to present on this is the wastewater treatment reference, which is in Sechelt, over on the Sunshine Coast. So this became operational, well, now, basically. We are in performance testing as we speak, and in the process of handing over that treatment plant to the municipality. The existing plant, which was called the Ebbtide wastewater treatment plant, was failing for various reasons. It was old, it was mechanically getting to the end of its life, didn't have the capacity that the community needed because of growth in the community, so it needed to be expanded, and it wasn't achieving the latest effluent quality standards, federal standards, 25 milligrams a litre TSS-BOD. The district of Sechelt decided that innovation was going to be key to their project. They wanted to really try and do the best they could. Not least because they had neighbours very close to the plant. And you can see in this photograph here on the left-hand side, my left, sorry, your right, houses literally across the street. So if you have neighbours that close, then you have to be careful. No nuisance. You don't want to upset your neighbours. So they set out with this mindset of greatest value. This wasn't about lowest cost to achieve compliance. This was what value can you get from a wastewater treatment plant? What about long-term economic, social, and environmental value? And that drove them to in various directions. Water reuse was certainly one of them, and this plant is designed to have the capacity to treat all of the average flow to effluent reuse standards, Class A. It also drove them to consider community value, integrating this plant into the community, no nuisance, providing an opportunity for education, for research, but also no fence. This is unusual, a wastewater treatment plant with no fence, so that the community can literally walk right up to the wastewater plant and look in the window and see what it's doing. These were the technologies that we installed. I should say that Veolia provided the complete treatment process here, from beginning, pre-treatment, and you see that with the fine screens and the grit removal, preliminary treatment, through to the secondary treatment step, which is the Organica process. You didn't need a primary treatment process for Organica, so you do pre-treatment and then straight into the Organica process, which some of you might have heard of. It uses plants to help with the sewage treatment. And you can see those in the photograph, hopefully, just about. Their roots dangle down into the process tanks and provide a surface for attached growth. So this is, again, a partially attached growth. It's a hybrid process. This uses suspended growth as well, this technology. After the Organica process is the X-Flow filtration membranes that I've talked about already, and then UV disinfection to get you to that very high standard. As part of our scope of supply, we're also providing various services, not least the process design and commissioning, which is fairly typical, but also a longer-term operational support role to make sure that this plant really performs over the long term. So we're not installing it and walking away. We're going to be there to support the district. So now switching gears a bit, stormwater treatment. Stormwater treatment is required in some places because where you have these very high flows as a result of heavy rainfall, your capacity in your system can be overwhelmed. That can happen in two places. Either at the treatment plant, where you can't put that much water through all those treatment processes, then you have to bypass it. Or it can happen out in the collection system in the sewerage network, where the pipes can't convey that much water, and then you have an overflow event. In either case, you're discharging untreated sewage into the environment, and that can be a concern. This technology addresses that concern. It's called high-rate clarification, and this is the active flow process that you saw the video of in Norway. It achieves secondary standards of effluent quality. Again, you can use it at any size, and that's important for stormwater because these flows, these peak flows, can be 5 times the average flow or more than that. So it's very, very high volume, large volumes of water happening when you have these heavy rainfall events. Key characteristic of this process is efficiency again, like the biological aerated filter, efficiency in terms of space footprint and therefore capital cost, but also efficiency in this process in terms of how quickly it's able to respond. I'll explain how that works with this. So how the process works is coming in from the left, you have the sewage. You add a coagulant to that, a chemical, and that destabilizes the particles, and then in the next step, you add a polymer, and that causes those destabilized particles to stick together. It's like a glue. So you end up with a flock, it's called, a little bundle of organic material. You add sand to that mixture as well, micro sand. I have a little bag of it here. It's very fine sand. And what that does is that sticks into this flock, into this jumble of organic material, and it's just like a little rock anchor. Sand is dense, flocks, organic material are not. So by sticking sand to organic material, it sinks like a rock, gives it a lot more density. So when you put it in the last step, the clarification step, this organic material with the sand just drops out very rapidly, and that gives you a very compact process. The sludge is withdrawn from the bottom of the tank in a pump and sent to a hydrocyclone. It doesn't involve any moving parts, it simply spins the water from the design of it. And what that does is the centrifugal forces cause the sand to separate out from the sludge, from the organic material, and the sand is put back into the tank. So you don't waste sand, you keep the sand, and the sludge then flows out into waste. This whole process takes less than 15 minutes to get up to full speed, and that's where that response time thing comes in. Very fast to respond, so it can handle those rainfall events. I mentioned compactness. This picture really says it all. So this is a very large treatment plant serving over 1 million people. It's down in Texas. Over 500 million litres a day of capacity, huge. And almost the same capacity in this little active flow plant down here in the corner. So you can see the difference in scale. Incredibly compact. But this does require chemicals, so you wouldn't want to run it just all the time because operating cost would be higher than the conventional methods. But for stormwater treatment, it's perfect. Low capital cost and very quick to respond. There are many of these processes all over the world, over 1,000 plants installed with the active flow process, over 120 in Canada alone. It's used for wastewater, and we saw that in Norway for clarification on wastewater. It's used for drinking water. There are 4 plants in BC for drinking water alone. Summerland, Metro Vancouver uses this process, and 2 First Nation communities up near Terrace, Windsilk and Geetonmax, for drinking water, and it's used for stormwater. Now 24 plants in North America. 23 of those are in Canada, in the United States. 1 of them is in Canada. It's under design at the moment. It's in Winnipeg. So the first of these applications for stormwater of active flow in Canada will be in construction soon. The reference I just wanted to talk about briefly, this is not so far from here in Washington State. This was one of the first applications of active flow for stormwater back in 2001. You can see the numbers there. This was because Puget Sound was used for shell fishery, so for the economic value it was important to the community to protect that shell fishery by ensuring the effluent quality discharge to Puget Sound was good. And so this is actually an overflow system where it's in the collection network. So the last technology I wanted to talk about just briefly is biosolids treatment. Biosolids can be a challenge. There are a relatively small number of things you can do with biosolids, sludge. You can incinerate them, but that causes some concerns sometimes with air quality, with emissions. You can apply them to land, but that can cause concerns with contaminants on the land. And I understand that in the Greater Victoria area, Capital Regional District has a policy of not allowing that. And really that leaves conventional options one choice, which is landfilling. And that's not a great option either. Nobody wants to landfill something because it's expensive and it has value potentially. This material has the potential to be reused. So you have to look for innovative solutions, and this is one of those. It's a thermal conversion process, in some ways similar to gasification. The process is flexible. You can treat different types of sludge with it. Here, the example I'm showing is after an anaerobic digester. So just to walk you through this, you have wastewater treatment happening, that makes sludge. You can then digest that sludge anaerobically to give you biogas and energy recovery. And then the sludge after digestion can be sent to the Athos process. This is our thermal conversion process. You don't have to have a digester, but if you want to recover energy, you can. You put oxygen into the process to encourage this thermal conversion. It happens at under temperature and pressure. And what that does is it breaks down the organic material into inert matter, and it produces a clean exhaust gas. And the reason for that is because it's not a combustion process, it's an oxidation process. After Athos, you then dewater the inert mixture that you've made, and the filtrate that you produce in that filter press step goes back to the plant. It's easily biodegradable, so it's not a problem to the wastewater plant. And you also get this material out of the process, technosand. Excuse me, I'm going to talk about that in just a moment. So as I mentioned, it's an oxidation process. The strict definition of this technology is wet air oxidation. It happens in a water environment. It's an exothermal process. It actually generates more heat than it uses, so you can recover heat from this technology. It's very compact, a hydraulic retention time of under an hour, and very flexible. You can use it for different types of sludge, variations in sludge. And you reduce the amount of material by over 95%, so the sludge coming in relative to the technosand going out. So a lot less material to deal with. But not only deal with, reuse. Technosand is inert. It is basically minerals, because that's what you're left with in sludge after you've got rid of all the organics. Silicon, calcium, aluminum, things like that. No pathogens, so entirely safe. It's a stable matrix. It's not soluble, so any metals aren't going to dissolve and cause any concerns. And you can reuse it for things like cement manufacture, construction. So the case study, very briefly, I should say this is an innovative process. There are 5 of these plants operating, all of them in Europe, none in North America yet. This is one example. The technology, the smallest plant that it's operating at serves 50,000 population, which would be about 25 million litres a day to convert it into those numbers. So it can be used at relatively small scale. This one is in the area of Milan, where they had an issue with biosolids. They were producing more of it, having more and more challenges getting it applied to land. So they looked for something innovative, and this is what they chose. They also had limited footprint and the potential to get support for the project, financial support from the European Union. They chose this technology because they found it was the lowest life cycle cost, meaning capital and operating cost over a long period of time, net present value type of an evaluation. This process has the capacity, this plant has the capacity to treat up to 4,300 dry tons a year. It receives sludge from 3 different treatment plants, so that's variability is an issue, and that's where this technology really helped. It can handle that variability. They found that it didn't produce any harmful emissions, and they have the potential to produce this much technosand and reuse that in the community. So with that, I'd like to wrap up. Just to summarize, I hope this has been useful for you. I hope there's something relevant in here for everyone in the room and everybody watching. I also hope I've been able to explain why I believe that technology is really core to a wastewater treatment plant project. How you integrate those technologies is very important. And with that, I'd like to thank you all for your attention and open it to questions.
So we've been very strict on the 1 hour, but we started a little bit late, but we have time for 3 questions. Other than that, again, to go to the Westside Solutions website, info, we're happy to entertain questions after. This isn't cutting into your time, by the way, I'm minusing it. Or directly to Veolia. So I saw, I didn't see your hand first, so I saw this hand first.
Chris, is that rap tune available on iTunes?
There's always a relevant question from you, Michael. Thank you for that. I haven't got a clue. But you can see the video on YouTube.
Yeah, a quick question. I have many, but I'll just stick with the one that's top of my mind in that last process. What's the general capital cost for that plant that was in Italy, and then the operating potential revenue or costs for running it? Keep it simple at that.
Well, I would have to say I haven't got those numbers to hand, so I'll have to follow up with you afterwards if that's okay. I'll take your details and respond with those details. What I would say on the cost perspective is that technology, there are various different ways of processing sludge. Applying it to land can be the cheapest if you've got readily available land. Putting it in a landfill can be cheap if your cost of landfill tipping is relatively cheap. So this might not necessarily be the cheapest if those options are available to you. But what I would say is if you're requiring to do something a bit more innovative than that, and you're looking at maybe incineration versus some kind of thermal conversion process, gasification or whatever, then this technology is going to become cost effective for sure. And as I said, they compared it on a life cycle cost basis and found it to be the most competitive technology available to them given their circumstances. They will follow up with specific information.
You said this is like gasification.
Yes. Expand on that?
If you could.
For sure. It's like gasification in that it operates under temperature and pressure. Specifically, a much lower temperature, 235 degrees Celsius is where the process operates at, around about 40 bar of pressure. That means that it doesn't do exactly the same as gasification. But I would say, comparing it to gasification, where it differs is that, well, a few things. You can use it just to process sludge. I'm not aware of a gasification plant that receives sludge only in its feedstock. I might not be aware of every gasification plant out there, but to my knowledge, there is no gasification plant that just receives sludge. Normally they receive things like wood waste and so on. Also, I'm not aware of gasification plants operating at relatively small scale where sludge is a significant component of the feedstock. So that would be another difference. Those 5 plants I mentioned, the smallest of those at a population of 50,000 population. So relatively small scale. And I don't believe that gasification plants work at that small scale. But in other ways it's similar. It's about reducing organic material into converting it thermally into other materials, partly to reduce the amount of material that you're ultimately trying to dispose of, but also to give you something that you can reuse.
Is there time for another one?
One more question.
Just
We need the mic.
then to follow up on that. So when this process is finished, what's left in that inert material?
So it's basically minerals. It's about reducing...
Put one more thing in, because we've been also learning here about the antibiotic-resistant organisms which have a DNA that's their trace thing. We'd like to know if that's destroyed.
Interesting. Endocrine disruptors, pharmaceuticals and personal care products, that kind of issue. I would love to have the same answer. In fact, I thought about that preparing this presentation for you today. The honest answer is I don't know what happens to those kind of materials. I'm going to call them endocrine disruptors for sake of a generic term, through this process, the Athos process. What I would anticipate, though, is that it's going to do a pretty good job of breaking them down because of that temperature and pressure. If it breaks down organic material to inert minerals, it's likely going to break down those kind of materials along the way because they're organic materials. I'm actually encouraging us to do a study on that right now, and potentially with the University of British Columbia, that over on the Okanagan campus, they have laboratory equipment for testing these things. So I would hope that we have the potential to do a study on that. Of course, we need the plant first, so we'll have to see how that goes, but maybe at pilot scale, for example. So As I say, honest answer, I don't know. I would expect that it'll do a pretty good job of breaking them down.
So thank you very much, Chris. So again, this is an awful lot of information to squish into an hour, but just to be fair to all our presenters, we say for an hour. And again, your questions, if you have follow-up, please send them through westsidesolutions.ca. And any information that you generate, Chris or any of the other presenters, we would like to share with the public as well. So to share with, so we can all have as much information as we can. So we're going to take a short break right now and reconvene at 2:15 for those in the room. There are snacks in the outside, and if you haven't already read the boards 42 times, they're out there for people to look at, and we'll reconvene in 10 minutes. Thank you very much.